Hello and welcome to Inside xtML, a learning series. Thank you for joining me. In this seminar, I'm going to talk about the ways a developer can customize a model compiler and show one such customization in action. This presentation is sponsored by xtUML.org. I invite you to join the community there to download open source modeling tools and interact with other application modeling enthusiasts. This presentation is part of a series of seminars by xtUML.org community members in an effort to broaden the knowledge of xtUML. So again, thank you for joining me, and I encourage you to visit the xtUML channel on YouTube to view recordings of the other presentations in this series. An earlier presentation from this series introduced the basics of model translation and gave developers an overview of the benefits and features of using a model compiler. Today's presentation is a follow-up to that introduction. We'll do a brief recap of the model translation process, then we will discuss the ways users can customize a model compiler. Finally, we will create and run our own model compiler extension. Let's begin by reviewing our high-level picture of the model translation process. The user creates their application model using the open-source xtUML editor. The UML diagrams they create describe components, these are the functional blocks, and the interfaces and messages these components use to communicate with each other. Inside the components, the developer fleshes out the desired functionality by creating data models, specifying life cycles and state machines, and implementing the operational processing in action language. The user provides application-specific translation settings via marking data. And the final input is the application-independent rules and templates that define the desired shape and structure for the application in the target language. These three inputs are fed into the translation engine to produce the optimized code in the target language. The model created in the xtUML editor is stored on disk in a SQL repository that conforms to a special model called the xtUML metamodel. The metamodel contains classes and relationships that capture the elements of the application. So, for example, the graphical model on the left has components, ports, and interfaces. These four components in the application are stored in the repository as four instances of the metamodel's component class. Each of these component instances is related to the appropriate number of port instances. For example, there are 2 ports on the location component and 1 port on the UI component. The port instances are related to the appropriate interface instances, and the interface instances are related to message instances, either operations or signals, which are not shown on this diagram. Since the model compiler operates on the repository data, model compiler writers must be very comfortable understanding and navigating the xtUML metamodel. Now that we have reviewed the model translation process and the underlying application model data, let's discuss what parts of the process are customizable. By modifying either the marking data or the rules and templates, developers can change the model compiler to output one of many target languages. You can change the details of the code generation within the chosen target language, that is, changing data structures, implementing various means of message passing, changing memory allocation strategies, or using debugging and tracing features, to name just a few of the possibilities. Model compilers can also be configured to output target code that complies with various standards such as MISRA-C, transaction level modeling, and AUTOSAR. If we expand our view to include supplemental data besides just the target code, we see that model compilers can also be customized and extended to perform documentation generation and to create application-specific artifacts to feed into other tools in industry formats such as XMI or IPExact. Now let's work through an example that extends the Bridgepoint model compiler in just this way. This example is meant to be fully reproducible, so I encourage you to revisit this presentation later on xtUML.org and duplicate this example at your own pace. In this demonstration, our model compiler customization will traverse the application instance data in the repository using the xtUML metamodel and output the data to an XML formatted file on disk. This example will use the trial or demo version of Mentor Graphics Bridgepoint. Bridgepoint includes the open source xtUML editor along with Mentor Graphics Model Verifier and Model Compiler offerings. The example extensions are located in the public xtUML models repository on GitHub. The first step is to navigate to xtuml.org in your web browser. Then use the link, click here under additional downloads, and that will take you to the download page. Once here, follow this link to go to the Mentor Graphics website to download the demo version of Bridgepoint. After you've downloaded the Bridgepoint demo installer, run the installer, and once the installation completes, use the desktop shortcut to launch the Bridgepoint application. Once Bridgepoint starts, you'll be presented with the welcome screen. From here, we navigate to the Quick Start. We're going to be using the example GPS watch application, so we click it to create it now. After the GPS watch project is created, we use the Help menu to navigate back to the welcome screen. Once again, we go to Quick Start, and then we create the xtUML metamodel documentation project. Now that we've created our example projects, I'm going to rearrange the views a bit to suit my own personal preferences. Okay, so now we're set up and we're ready to continue. Let's start by taking a look at our example application model, the GPS watch. The library package contains 4 components. Each component has ports and interfaces. In the normal operation of the model compiler, these components are translated into implementation target code. Now we've decided that we want to create a model compiler extension that represents these components, interfaces, and ports in an XML formatted file. To do this, we're going to have to traverse the xtUML metamodel. So let's open our metamodel project, navigate to the component package, and right here is the component class in the metamodel. You can see it's connected to a port class across relationship R4010. So from this we know that our underlying data should contain 4 instances of the component class, and each of those component instances will be related to the appropriate number of port instances across this relationship. We're going to extend our model compiler by editing a underlying file in the project, one of the inputs to the model compiler, the system.mark file. To do this, we need to switch perspectives to the C++ perspective. From here, we open the gen folder and open system.mark. I mentioned earlier that our examples are stored on GitHub. So let's switch over to GitHub and pull the example data down. So I've navigated into the example 1 file, and then I'll just copy this information. And then paste it here. So now our file data is in the system.mark file. Lines and commands that begin with dot are special input to the model compiler. So you can see we have comments here, and then files that do not begin with a dot are output to the console or to the file when we later use this emit to file command. So the first thing we do here is select from sys our instance of the system itself. This will give us the handle to the top level GPS watch instance of the system. And now we have many components in our library package. So we will select these component instances from the component class, which has key letters CC. So you can see that right here in the meta model. And then we loop. So for each of our component instances, we will spit out this XML information which contains the component name. And this is a special substitution variable which uses the instance data and then accesses this name attribute from the component instance. And then each of the components has ports, so we will select into a set of ports across the R410 relationship that we saw earlier from the component instances to the port class, and that will give us a set of each of the ports that's related to the component instance that we have in hand. And once again, we will spit out XML information about the port name. And we will loop. So for each of the component instances, we will do this iteration, and then we will emit all this data to an XML file that's named with our system name. So now we're ready to actually run the translation process and use our model compiler extension. So let's save this file. Now I don't really care at this point about the code compilation, so I'm going to access the properties and the builders, and I'm going to turn off the builders that I don't care about and just leave the model compiler pre-build in the model compiler builder. And then now I'm ready to build the project. You can see the translation process running in the output. And then under the code generation folder, we now have an XML file named gpswatch.xml, and you can see that it contains 4 components. If we look at the source itself, you can see that we've iterated each of our components, and for each of the components we've outputted the port underneath it with the appropriate name. So what we have achieved here is an exciting first step where we've accessed the underlying model instance data and extended the model compiler not only to output implementation target code, but to output the data in an XML format, which we can continue to massage into a form that might be useful for documentation or for feeding into some other downstream flow. Next, let's look at how we can continue to enhance our extension to access and take advantage of more of the model instance data. To do this, let's go back to our system.mark file and remove the example1 data. And then we'll go back to GitHub, and if we traverse back up to the examples folder, we can find example2. We will open this and copy this data. And then paste it into our system.mark file. Now let's switch back and explore our component diagram a bit further. So the component is connected to a port, and a port is connected to an interface reference across our 4016, which we see here. That interface reference is connected to an interface, which is connected to an executable property. And that property is subtyped by an interface signal or an interface operation. So these interface operations and signals are the messages that go across the interface through the port. Therefore, if we want to extend our XML output extension to output the message names for each port, then we will have to traverse through this path down to the interface operation or interface signal instances. And that's what you see here. So this is the same iteration of the ports inside of our component instance that we looked at previously. And from the port, we traverse to the interface reference and get an interface reference handle. And then from the interface reference, we traverse to the interface. We traverse then through the executable property, and from the executable property instance, we traverse either to a asynchronous signal, which is the interface signal, or the interface operation. Now, each interface can contain many messages. So when we do our selection here, we're selecting many executable properties out of that instance itself. And then we iterate over each of those instances of executable property and determine what the correct subtype is. And we add protection here by doing a selection and then checking if the instance handle we got back was empty or not. So now let's run our model compilation process again by building the project. And this will allow us to test the functionality of our updates and enhancements. So the process runs, and then if we open our GPS watch XML file, we now see that the messages are output along with the port information. So in this case of the heart rate monitor component, there's the HR port, and inside that port, these messages, heart rate changed, registered listener, unregistered listener, are the messages that can go across the port and the interface. And you see the same for all of the components, ports, and messages. I hope now that you can begin to see the ways that this extension could be enhanced even further. We could modify our XML output to include the type of the message, for example, the interface signal or interface operation. We could include the actual interface names themselves. We could enhance the message output to include the parameters to the messages and their data types, as well as the return type for the operation. We could also traverse from the component instances down inside to the packages and classes that they contain and explore the attributes and operations on those classes. So there's really the only end to how far we could take our enhancement is the model data itself. Any data inside the application model is available to us now. And we could enhance this XML output to fully explore all that model data, and we could even change, as I mentioned previously, the format of our XML to conform to industry standards such as the XMI data interchange or the IP exact, which helps define the modeled components as hardware components and bus interfaces. As you continue on your own to enhance the customization we have started, you may find that you need to take advantage of the additional features or constructs of the rule specification language, also known as RSL, that we've been using. Bridgepoint includes documentation in the help system. Under Bridgepoint UML Suite Help, Reference, RSL Reference, RSL Overview. This documentation describes all the features and syntax that are available to you as a model compiler writer. This concludes my presentation on customizing a model compiler. I hope you have found the information instructive and that you see the exciting possibilities that are available to developers who are able to customize and extend model compilers. I invite you to look for our next installment in this Inside xtUML learning series, and I look forward to participating with you in the xtUML.org community.